Good afternoon, morning, day to everybody. We are now on to section 3.6, chain rule. And chain rule kind of begins when we kind of ask this question of how can we differentiate y equal to some function of x, which is sine of x squared minus 4. How do we differentiate that? I have a function inside of another function. I don't know. So this function is, if you remember from chapter 1, it's a composite function. Remember we wrote those like f of g, that little like circle. So in this case, y equals f of, let's call it u. And we'll call that inside function u. So we're going to have sine of u, and u is going to equal another function of x. Let's call it g of x. So that's going to be x squared minus 4. So I think of green when I think of g. So g of x here is going to be this inside function where f of x is going to be this little sine function. And that last little parentheses too. Alrighty. Wow, I love those colors. Cool. So we have our composition right here, but I still don't know how to take the derivative of that. So we differentiate, right? Remember, differentiation means, hold on, I have to concentrate spelling this word. Differentiation, or asking to differentiate, means taking the derivative of. So we differentiate using what's called chain rule. Right? So let's look at a little simpler one than sine and view. So in this example, we are going to use y is equal to 3x squared plus 1, that whole thing squared. And we want dy dx, right? Y prime. And it's really important in this case to call it dy dx because what I'm about to show you. So if what we do like we did before, we're going to call y equals some function of u, and that is going to be u squared. So in this case, this squared part is my outside function, my f, and u equal to g of x equal to the inside, so 3x squared plus 1. Let's call that guy green. Beautiful colors together. Maybe I'll switch these up later, who knows. So we have something like this. If I take the derivative of y equal to f of u, which is u squared, then I will get dy du, derivative of y with respect to u. In that case, I know from power rule this is just 2u. If I take the derivative of u here with respect to its variable x, I'll get du dx. Right? We learned that in the first section of derivatives. This just means the derivative of u with respect to x, derivative of y with respect to u. Okay? So again, from power rule, I know that this is going to be 6x plus 0, so just 6x. Alrighty. Well, if I multiply these two things together, dy du times du over dx, well, du over du cancels out, and I'm just left with dy dx, which is what I wanted. So if I do that down here, I'll get 2u times 6x, which is equal to 12ux, but I need this. This just has x and it doesn't have u. So I'll go back up here. What did I call u? I called it 3x plus 1. So I'm going to do like 12x times 3x squared plus 1. And I can take that one step further if I wanted to and distribute. So what is that? 36x cubed plus 12x. Yeah, that sounds right. So we could have kind of ignored chain rule if I wanted to and FOILed. And we would have gotten the same answer. It's gotten a word. Whatever. Okay. So you guys are welcome to try that on your own. Not really feel like foiling right now. So it's just kind of what we call chain rule. So we saw in this little section the chain part of it, right? How I can call something else just one letter, another variable if you want, in the function and make two different functions, and then I can multiply together. Those are chains. All right, so this theorem 3.6.1 is called chain rule. It's weird that it's a theorem, but you know, whatever. So it says that if f of u is differentiable, remember DIFF, at the point u equal to g of x, and g of x is differentiable at the point x, then their composition f of g of x, which remember we can also write it this way, which is my favorite way of writing it. I also think fog is a function. That's also differentiable. And the derivative of this composition, well, that little x needs to be there. There we go. The derivative of it is going to be f prime of g of x times g prime of x. Alrighty, so what are some cute colors? I like this blue. So right here, this is the derivative of the outside with the inside still the same. And then, ooh, blue and orange, not a fan. G prime is just the derivative of the inside. It's sometimes hard to see the inside and the outside of function, and we'll go through a few examples, and obviously you'll have homework to be a better practice as well. So don't beat yourself up if it's a little difficult. I sometimes also fumble finding the inside and outside functions. Just know parentheses are your friend. So another way that I like to remember chain rule, because it is common to write, if I have f of g of x, it is not equal to f prime of g prime of x. Big no. Don't ever do that. I will be very angry. I'll be very sad too. Alrighty, so this is how I like to explain chain rule, and I like to call it fishful thinking, like wishful thinking, but it's called fishful thinking. And why I like to call it that, I just made that up, but I'm going to keep calling it because fishful thinking is hilarious. Okay, cool. So my mom told me this story when she was a girl, and she went fishing with my grandfather, her father, and caught her first fish. And his rule was that if you caught a fish, you had to skin the fish yourself. I'm sorry if you are not down with the story. Anyways, so my mom caught a fish. Oh my god, terrible fish. Okay. So she caught her fish, and when you skin a fish, you have to cut into its belly. If you can't, like, you have to cut into its belly, right? If you can't, like, hacksaw in half. That's not how you cut a fish. You're gonna ruin all your fillets. It doesn't work like that. You just have to cut it on its belly. Well, when she did that, there was another fish inside of the fish already. So she didn't have to just skin one fish, she had to skin two fish. So if we call this big fish Fred, and we call this little fish George for F and G, then we have to first cut into Fred, but George is still in there hanging out. And then we can cut into George. All right? And that's the fishful thinking. It's one of my favorite ways to explain this. There's some like hand movements too of kind of explaining like something inside of something else, like holding your fist. But fishful thinking is kind of my main way of explaining chain rule and remembering it. You can't hacksaw your fish in half. Some people like to explain it like onions, like you take it off by, they have layers, but you chop an onion in half. No one cuts it by layers. That's silly. I don't like that explanation. Fishful thinking, totally my favorite. And I made it up. So rad. Okay, cool. So let's do let's do kind of an explanation. So we can also write the derivative with respect to x of some function that doesn't have x that we know about in it. So it just has u. We don't always know anything about u, so we have to assume that its derivative may have a unit. So we write the derivative with respect to x of f of u equals f prime of u times du of x. You'll see this is how the rest of derivative rules are going to be taught. So basically, when you see a derivative rule, it's not going to be with respect, there's not going to be an x involved at all. It's going to be a u, but you're going to be still taking the derivative with respect to x. All right, so let's talk about a fun little example. And so we're given y equals sine x squared plus e to the x, and we're asked to differentiate with respect to y. Alrighty? So there's lots of different ways to do this. Some people like to just call like u equal to x squared plus e to the x, and then they'll have like y equal to sine of u. So then what I like to do is I'll write y prime is equal to cosine of u times u prime. That's the same u prime we can just call du dx u prime. And then what's u prime? Well, I go back up to u, I find its derivative, I use power rule on x squared, that gives me 2x, plus I know e to the x's derivative is just e to the x. Coolio. So then I can plug that in. I have cosine of u times 2x plus e to the x. Careful here. I need to add a parentheses around here. I'm only multiplying cosine by 2x. And then you need to be careful because I was given a function of only x's, and so my answer needs to only have x's. I can't only have u's, so then I'm going to plug in u in, x squared plus e to the x, 2x plus e to the x. Some people are, after practice, you guys will be able to hopefully not have to use u and you can kind of see it, but sometimes I like to just rewrite a function still today if I'm taking derivatives to really separate and make sure I can see my chains if I'm making chain rule, if I have to use chain rule. Okay, so we talked about how derivative rules are going to look a little different when we have some u in it. So we know that e to the x's derivative is e to the x. And that's like a really cool property about e to the x. But what about e to the u? Or more likely, the derivative with respect to x of e to the u. Well, if we use this notation up here, we're going to e to the u is going to stay, because that's the derivative of e to the something, is e to the something times du dx, times the derivative of the inside. U is technically my inside function here. I can then also just kind of rewrite that as e to the u, u prime. I like to use primes. You'll see in the next section why, just because dy over dx or du over dx, it just takes a lot of time, takes a lot of space, that's all it is. But it's very useful to also write du dx to know what you're taking the derivative of with respect to. It gives you a lot more than just u prime. Alrighty, so using that new knowledge, let's do an example. So we're asked to find y prime when y equals e to the cosine x. Alrighty, so let's just try to one and done it. So we can just y prime it. So then above I know it's going to be e to the u, so whatever I started with, so I'm still going to have e to the cosine of x. Let me write this down a line, give myself some space. Okay, so we're going to have y prime, e to the cosine of x, right? That's going to be e to the u times u prime. So looking at this, what is u? U is going to be cosine of x. So u prime, since we know the last chapter of this, negative sine of x. Alrighty, so make sure the textbook had that right. There we go. And then we're done. You could simplify it if you wanted to. Just given like negative e to the cosine of x, sine of x. Doesn't really matter. Alrighty, so what if there was a third fish? Henry. He's inside George. So then we would have like f of g of h of x. Well, we can still call not y, u, this one's y, call u g of h of x, and we can call w h of x. So that u would be, y would be f of u would be g of w, and w would be, well, it would still be h of x. So if I took the derivatives, I would get dy du, du, dw, dw, dx. And if I multiply all those together, dy du times du dw dw dx. So these two cancel out, these two cancel out, and we get dy dx. Yay! So we can just add one more fish in there. It doesn't do anything unsuspected. And it would kind of go on like that forever. That's why some people like the onion analogy. Again, I think fish is better. So let's do an example with that. So we were asked to differentiate with respect to t tangent of 5 minus sine of 2t. Other parentheses. Alrighty, so I think f we used as, what color was it? Maybe this one. So our f here is going to be tangent. That is not my highlighter. Tangent, and that parentheses. And then g is going to be 5 minus sine, it's parentheses, and then my most inside function is going to be 2t. Parentheses are really helpful in this time. And I actually sometimes draw in some more just to help. So let's call y tangent of u. Let's call u 5 minus sine of w, and we'll call w 2t. Now you don't have to do this every time. Some people can just look at it and go down the time. You can even call these f and g and h if you want. This is just one way to do it. Alrighty. So dy, oopsies, dy du equals tangent's derivative is secant squared of u. Du dw is going to be, we know sum and difference rule, that the 5 is going to go away, and then I can add the derivative of minus sine of w, which we know is minus cosine of w, and then dw dt is just 2. Well, from above, I just saw that I can just multiply all these things together. So I get that dy dt equals secant squared u times negative cosine w times 2. Well, my question gave me something with t in it, and now I have u and w. So now I have to go back and plug in everything that has a u and a w in it. So that's going to equal secant squared, what was u? It was 5 minus sine of w, and w was 2t, times negative cosine of w, which is again just 2t, times 2. And we're done. If you want to simplify it, you can just bring this negative 2, take that negative and the 2, and bring it up front if you want. Alrighty, so I want to do a few examples from the textbook because I want to show you, I think these three are really good examples. So our first one is going to be 3.6.23. And we're asked to find dp dt when p equals the square root of 3 minus t. Alrighty? So I'm going to write this problem a little differently. This is a different way to think about it. So if you don't want to write the chains, this is another way we can do it. So I'm first going to rewrite this just to help me take its derivative. So I'm going to do 3 minus t to the 1/2. Alrighty. And then I can take the derivative with respect to p, and this 1/2 is going to come down. Right, so I'm taking the derivative of the outside with the inside, still the same. The inside here is 3 minus t, it's inside that parentheses, minus 1/2, because that's how power rule works, times the derivative of the inside. So it sometimes is nice to do it step by step. Take one derivative at a time. It might feel a little overwhelming to take a lot of derivatives in one equation. You might fumble over yourself. So that's why sometimes we write it like this. So then I can write p prime as 1/2 3 minus t to the negative 1/2. And then I can simplify d dt of 3 minus t to do what? Okay. So second step was taking the derivative of the outside with the inside still the same, times the derivative of the inside, and now we're actually going to take the derivative of the inside. So 3 is going to go to 0, minus t, and that's going to give me just a -1. Now I'm done with calculus. Not really, I still have a semester to go. So now I'm just going to simplify. So then p prime, I'm going to rewrite, this is going to be negative, we'll do this in 2 steps. So 3 to the t to the negative 1/2, I can write as 1 over the square root of 3 minus t. And then I can put that all together since fractions are top times top, bottom times bottom. And that'll just give me negative 1 over 2 square root of 3 minus t. Remember, both of these answers are acceptable, just showing you a more simplified way. Alrighty? If you get here, my heart will be oh so happy. If you get here, my heart will just be as happy. Alrighty? And there you go. Whoopsies. Okay, so our next example is, a really good one. Problem 3.6.15. And we're asked to differentiate y equal to secant of tangent of x with respect to x. That's what WRT means, with respect to. Okay, so I like to use not use substitution, but using the u, w, and whatever with this one. And I'll show you why. So let's call y equal to secant of u and u equal to tangent of x. All right, so dy dx is going to, sorry, yeah. So that means that, yeah, dy du equals secant u tangent u. This is why I like to do it, because you're multiplying two functions together, and that inside function is going two different places. It's going with the secant and the tangent. And then tangent's derivative is secant squared x, right? So let's combine them. So I'll get, dy du times du dx, because that'll give me dy dx. So we get secant u tan u times secant squared x. Don't think that you can combine these two secants and be like, oh, it's secant cubed. No, this one is secant of u, this is secant of x. Two different things. So then that's going to equal, when I put in my u, secant of tangent of x, tangent of tangent of x, times secant of x squared, or secant squared of x. Alrighty? And that's our final answer. That's why I like to use u, because secant's derivative is secant x tangent x, but in this case it's secant of the inside times tangent of the inside. Alrighty, so last example is an example of kind of why I like to sometimes add parentheses, and I've done this problem before and kind of forgot where chain rule came in. And I want to show it to you all so you have experience with it. So if I am asked to differentiate y equal to x squared sine to the fourth x plus x cosine to the negative 2x. So first thing I'm going to do is I'm going to rewrite this. Let's do it right, yeah. I'm going to rewrite y to see my inside and outside functions. Alrighty, so we're going to rewrite, and we're going to call this y equal to x squared times parentheses sine of x to the fourth. That's the same as this little guy right here. Sine and the 4 above the n, same with this negative 2 above the s in cosine, means that the sine function is to the fourth. They write it like this so you don't think x is being raised to the fourth. So then we have x times cosine of x, and that quantity raised to the negative 2. So now I have to do chain rule when I'm taking the derivative of this sine and with this cosine. All right, So first, let's do product rule. Because I have a function of x, something with x in it, times another something of x in it, plus something with x, times something with x in it again. So we're going to have y prime equal to, let's take the derivative of x squared. So that's 2x times, and I'm going to keep sine x to the fourth. So sine 4x plus, now we're keeping x squared, it already did its job. And now we're going to take the derivative of sine to the fourth. So power rule says that 4 is going to come out front. And I'm going to have sine of x cubed. Right, so the 4 came down up front, sine's my inside, something to the fourth is my outside. So I have to do the outside with the inside still the same, sine of x is still in there, times sine's derivative, which is, right, cosine of x. Good job. Alrighty. If you're a little confused, don't worry, we're about to do it again. Plus, let's take x's derivative here and keep cosine to the negative 2. So we're going to do, that's 1 times cosine of x to the negative 2 plus, we're going to keep the x. And now what's going to happen is cosine's my inside function, so I'm something to the power of negative 2 is my outside function. So take the derivative of the outside with the inside still the same, so it's negative 2 cosine of x to the negative 3. Remember power rule, the exponent drops down, it becomes a coefficient, and then I subtract 1 from the power. Negative 2 minus 1, that's how I got the negative 3 right there. So then times cosine's derivative is negative sine of x. Beautiful. Now we're going to just simplify a little bit. So I got 2x sine to the fourth x plus 4x squared sine cubed x times cosine x plus cosine the negative 2x plus, not plus, oh yeah, plus, because this negative 2 and this negative sign, those cancel out, so we just get 2x cosine to negative 3x sine of x. Alrighty, so let's take a second and roll through these again. So my outside function for my first terms are separated by a plus and minus. So x squared, we're not really looking at him right now just because I know it's product rule, so I have a function of x times another function of x, which is the sine of x to the fourth. So if I'm just focusing on sine of x, that whole thing to the fourth power, the fourth power is my outside function, and my inside function is the sine of x. So here is sine of x, and there's its derivative, cosine of x, and here is something to the fourth power's derivative right there. If we go look at cosine to the negative 2, then something to the negative 2 is the outside function, and cosine of x is the inside function. So then, oh, I like that. We move it down here. Remember this first term of the second line? We didn't take the derivative of cosine of negative 2x because that is how product rule works. I take the derivative of one and I hold the other one there. So then we can see that this is the derivative of that negative 2 power oops, what color was I on? There's cosine still being there on the inside times cosine's derivative. It's so beautiful when it's colored. Alrighty, so, and then we simplified right here. Simplified. Alrighty, so those are all the examples I had today. Chain rule is kind of where a lot of people find like what method works best for them. Do you like choosing U and W and so on? Can you just kind of look at it and be like, okay, cool, this one, and then block out that part, block out the red, and then, okay, green part. Okay, cool, moving on. Now I'm just focusing on this like bluish gray. Cool, took that derivative. Now I'm going to take the derivative of purple, and so on. Just please, please, please don't take the derivative of the outside function with the derivative of the inside function inside. Not cool. So for the last time, I'm going to write it again. F of g of x, that derivative is equal to f prime of g of x, the derivative of the outside with the inside still the same, times g prime of x. It is not f prime of g prime of x. It is never that. Don't ever tell me that. I will cry. You just cut your fish in half and you ruin dinner. So please don't do that. Okay? That's all I have for this lecture. I will see you in